Okay, well, from what I hear, this is about what, on average, the number of students finishing Math 1414. Most instructors that I've talked to have about 8 to 10 people left. It's pretty dire, but I think they're just people who aren't here today, but must be that week before finals, right? So let's talk a little bit about the final. I know I already told you when it was. If you go to Canvas, go under Files, and then go under, I think it's like Exam Solutions or something like that. You will now find something that's called 1414 Complete Exam Solutions. It has exam 1, 2, and 3, all 3 exams with the key, so you can go back and begin to review. All right? So just be aware of that. It's there. Next class, I plan on reviewing for the final. So I want to answer any questions. Yes? What's that? The final? Yeah, pretty sure. Tuesday. Yep, normal time. Normal start time, but the exam actually goes from, let's see, the 12th. Yeah, so our final is Tuesday, May 12th, 11 a.m. to 1:45 p.m. That's the difference. It's a longer class. All right. So again, make sure you go look at the solutions online because I've got them all there for you. Now, of course, those, if you review the exams that we've done, that'll take care of part of the final, but there's still stuff, systems of equations, some matrices and stuff I'm going to talk about today, and that's it. So today will be the last day of new material. All right. So let's go and talk about a system of equations. We talked about matrices last time, didn't we? Okay, so what I'd like for you to see is some different notation for solving systems of equations using matrices notation or matrix notation. So let's say, as an example, I wanted you to solve the system. Where's that sheet I had? What if we had 3x plus 4y equals 6, 2x plus 3y equals 5. So, today is really about exposing you to stuff that you're going to see later if you do take more math. All right, it's not, there's no way we can master anything over one course, one day, right? But at least you've seen it before. That's what I'm going for here. So this is what we had done in the past. That's the way we represented a system of equations. We had 2 ways of doing it, right? We could do substitution or elimination. You seem to favor the elimination from what I could tell, but here, if we did elimination, we'd want to try and get what, maybe the x's to go away or the y's. It would be up to you, right? So let me show you now matrix notation. So matrix notation would look like this. We draw a big bracket for the matrix. We write 3, 4, 6, 2, 3, 5, close the bracket, and then we usually put a line here or a dotted line. I think I said I was going to use the solid line. This is what we called, anyone remember what we called it? Augmented matrix. The augmented matrix represents a system of equations. Do you see that it's just this, but you just don't write the x's and y's and you don't write the equal signs, right? So we want to keep in mind that this column of numbers represents our x's, this represents our y's, This represents like an equals, and this represents the constant or the number that's on the other side of the equation. So when we use this notation, we can do everything that we did before. All right? Just don't have the x's and y's in the equals. All right? Question? So what I'm going to do is I'm going to look at this column here, and I'm going to say I want to make one of these numbers become a 0, which was equivalent to me saying let's make the x's go away, right? So what could I do to make one of these become a 0? Or to make these x's go away, what did we have to do? Multiply the top one here by maybe 2 and the bottom one by -3, right? They have to be opposite in sign. So we would do the same thing here. We would multiply this by 2. We'd multiply this by -3. And then we would rewrite the entire matrix, all right? So the entire matrix would now become 6, 8, 12, and then -6, -9, -15. Are y'all with me on that? So, I mean, it's really nothing new here. It's just different notation, different way of writing the same thing we've been writing. And now at this point, we would add those two rows together, wouldn't we? So I'm going to add these two rows together and replace the second row with that. So what's my new second row going to be? Careful. 0, -1, -3. And then what about the top row? I can do 6, 8, 12. I could even do -6, 9, -15. I could even do 3, 4, 6, or 2, 3, 5. Any of these, right? I'm going to go back to the original one, 3, 4, 6. And at this point, we're pretty much there, because doesn't this tell me I know what y is? Right? What is this saying? Make both sides positive, because you can multiply by -1. That's saying y is 3, isn't it? That says y is 3. And then once I know what y is, I can come back up here and I can get what x is. Do you kind of follow that? Okay, now, I multiplied both sides by, I multiplied everything by -1. Just put a -1 multiplied through just to make it look like y equals 3 instead of -y equals -3. I could have rewritten the matrix. I was trying to avoid that, but I will do it. There. So this means y is 3, right? And once I know that, I come back up. What does this first equation say? 3x plus 4y, but what's y? Must equal 6. Okay, so I use that answer to rewrite this first equation, and now I can solve this for x. So what's x? -2? So how would I write my solution? It's an ordered pair, right? What goes first? X, -2, and then 3. That would be your solution. Now there are more things we can do with matrices. We can investigate this thing called a determinant. And there are other ways to solve systems of equations other than the elimination substitution. There's a thing called Cramer's rule, which is a very nice little shortcut. But due to time constraints, we really can't get into it too much. It's the next 2 sections of the book that I'm not going to, well, it's not even on our schedule. But a lot of times in high school, they just teach the students Cramer's rule. And there's no like understanding really of why or what. It works and it gives you an answer. So I just want you to be aware of that. It's out there. What I do want to show you though is something called a determinant. And again, this is just exposing you to it so you can say I've seen a determinant. I haven't seen how it's used, but I've seen what a determinant is. So we'll do a new page here. I need to figure out what node I'm on. Let's see, last class. 12.2.2. Any consensus? That's where I was, right? So 12.2.2. We'll make this one right here 12.2.3. And then the next one, 12.2.4. Yes? Why? Oh, did I not? Oh, really? I hadn't posted? How about the videos? Okay. Videos are there? Okay. I just may not have uploaded the notes. I will, though. Okay, so determinants. Trying to figure out how far I want to go into this. All right. Okay, last time we talked about what we meant when we say 2 by 2 like this. This meant we have rows and columns, right? So this means if you have a matrix that has 2 rows and 2 columns, if your phone's that important, just take it outside, okay? Okay. I mean, I don't mind you doing it, just not in here. Okay. All right, so we have a 2 by 2 matrix, right? A, B, C, and D are just numbers, right? When we say determinant, it's a calculation we can do with these numbers. And it's a very simple calculation, right? The determinant of this matrix is, first of all, the way we represent it is kind of tricky. It looks very much like this, doesn't it? I mean, the matrix is a bracket, though, isn't it? If I just put lines, it's almost like an absolute value. Okay, it's not an absolute value, but that's like the symbol we're using. This represents the determinant of that matrix, right? That's telling you this is the determinant. Now here's what it is. It's A times D minus B times C. That's all it is. You're going to multiply 2 numbers together, then subtract 2 other numbers multiplied together. And you can kind of see it. It's this times this, A times D, so diagonally down, minus B times C. Just remember the minus, all right? Remember the minus. So let's just do an example. This really is not complicated, all right? I don't want to make it complicated. Find the determinant of this. 2, 3, 5, 7. So there's a 2 by 2 matrix, right? There is a way to get a determinant of a 3 by 3 and even an n by n. It gets a lot more complicated. Okay, so we are not going to, well, we might do the 3 by 3. I don't know. Just we'll see. Let's see how this goes. The thing is, I'm not showing you what you can do with the determinant. The determinant is very, very useful, but it's just, I think it'll take too much class if I actually get into it. I tried to show you last class. Someone was asking, like, why are we doing this, right? There's a way you can multiply both sides of a matrix equation by something to make it go away. It was like, and it requires that you have the determinant to do it. So We aren't going to do it, but you should be able to tell me what the determinant of a matrix is pretty easily. So what is the determinant of this? Of a 2 by 2, yeah. What is this? 2 times 7 minus 3 times 5, which is 14 minus 15, which is -1. That's it. All right, that's it. So not much to that, right? You'd probably be okay if I gave you a final with like 30 of those and just. Okay. Well, maybe we should do the 3 by 3 then, so you can see it. You want to try it? Let's just see how you do with it. Yes. What's that? This? That would be given. That's matrix notation. I'm not sure what you're asking me. This problem I did before, we call this an augmented matrix when it's actually coming from a system of equations. And that's why we put the bar there. The bar lets you know this was like originally an equation. You could just make a matrix out of just these numbers right here, right? 3, 4, 2, 3, and that would be a 2 by 2 matrix. But it's not an augmented matrix. So this is just saying, hey, if someone gives you a 2 by 2 matrix, can you find a determinant? Yes, here it is. Okay? So let's try a 3 by 3, and let's just see if you get ill when you see it. All right? So 12, 2, 5. Determinant of a 3 by 3 matrix. All right, so first let me write down what the 3 by 3 matrix would look like. Now, how many entries am I going to have in here? 9 of them, right? So I could do A, B, C, D, E, F, right, and use all these letters, but what about I use this instead? Remember this? A11, A, what would be the next one? 1, 2, A, 1, 3. What was the first number representative of? The row, and then the second number was what column you were in. So then I could have A, 2, 1, A, 2, 2, A, 2, 3, and then finally A, 3, 1, A, 3, 2, A, 3, 3. All right, there's a 3 by 3 matrix, right? A general 3 by 3 matrix. Hey, notice along the diagonal, notice there that it's always like 1, 1, 2, 2, 3, 3. Like if you had a 4 by 4 matrix, the diagonal would be 1, 1, 2, 2, 3, 3, 4, 4, right? Just pointing it out. It's obvious, but I mean, again, that diagonal becomes very important later, all right? All right, so what's the determinant? You would hope that it would be as simple as the last one, and it kind of is, but there's a lot more numbers to work with here, right? So I'm going to write down the formula the way it appears in the book, and then let's actually look at it from a different perspective, because there's easier ways to approach it. So here's the formula. I'm going to just write it out of the way it appears in the book. And let me see if you, oh, I need the determinant of this. So how do I say determinant? I have to put the bar around this to say determinant. All right? I want the determinant of that matrix. If I just write the matrix, that's not the determinant. The bars represents the determinant. So here's the formula. A1 bar A22 A23 A32 A33. Just write it down, okay? A12 A21 A23 A31. Are you sick yet? A33. Last one. Plus A13 A21 A22 A31 A32. Okay, now the reason why I'm sitting here holding the book in my hand doing it is because I don't really have it memorized that way. That's not the way that I think about the determinant of a 3 by 3 matrix. And I don't even think that's something you should think about when it comes to the determinant. But that's a formula if you like formulas. Now let's talk about what it's saying. It's saying you're supposed to take A11, which is a number, isn't it? And multiply it times this thing. But what's this thing? It's a 2 by 2, and it's the determinant of a 2 by 2. So you would have to take the determinant of this matrix, which means you'd have to do that little diagonal multiplying thing, you know, get that determinant, and then multiply that number times this. Then you do minus, so the sign switches to minus. Now you do A212, which is this one, and then the determinant of these things, okay? Understand kind of what's happening? All right, now let me show you a different approach, all right? I can't quite get that down here. Let me move it down. I want to move this down so you can still see my formula down there. Okay, so here's the way that I look at it, and a lot of people do. Oh, before I do it, the determinant is a number, right? This is a number. This right here is a determinant, so that's a number. Number times a number is a number. Then you have number, number, put them together, subtract, you still have a number, number, number. So the determinant is a number, all right? So if I want to get the first part, there's 3 parts, right? 1, 2, 3, 3 parts. If I want to do the first part, what I'm going to do is, remember, I'm going to start with A11, right? That's this top one. And I'm going to, A11, I'm going to cover this up, okay? Like this. And I'm going to do the determinant of this bottom corner here. See that? That's this. You see it? So I'm actually physically going to cover this up. Well, I write down A11 first, and I cover up everything, and I just do the determinant of the bottom 4. Yes? Then, when I go to the next one, I do A12, right? Cover up the middle. Sorry. Cover up the middle, and look at the bottom 4 now. You see the bottom 4 of these two and these two? That's this. You see it? Then when I do A13, I'm going to do that, write it down, and then cover up that column, and then do this determinant of these bottom 4. Make sense? Now you have to practice with it. And also notice, it's A11, the next one you subtract. So, you know, you change the sign. So it's positive, then negative, then positive. And that's just the property of the determinant. It always does that. And then when you get to like 4 by 4, 5 by 5, we have a general formula that's pretty ugly, which you probably would not see for quite some time. All right? Like, you won't see it throughout the entire calculus sequence. You won't see anything past the 3 by 3 determinant. Okay, so let's do a determinant. Let's see how this works out. It's not so bad, right? Well, let's do one, and then you can tell me if that's not so bad. Okay, so this is already in notation that we want, right? That's the notation we like. It's got the determinant already there, so I'm asking, what's the determinant of that 3 by 3 matrix? I didn't necessarily have to put in the matrix notation to tell you it's a matrix. It's kind of implied, all right? So let's see. First thing I'm going to do is write down what number? 2, right? 2 is the first thing I go grab. So I write down 2 times. Now, I need to do, since I'm doing the 2, I'm going to hide this column, right? I'm going to act like that column's not there. I am going to do the determinant of the bottom 4 numbers I see here, which is going to be what? What's the determinant of this little 4 by 4 or 2 by 2 matrix right here? Let's do it slow. It's 2 times 1. That's this, like this, right? Then minus what? Negative 3 times 0. Make sense? Yes? But the negative 3 times 0 is just 0, so all you really get here is 2 times 1, which is 2. So you get 2 times 2, which will be 4, won't it? I'll do that on the next line. Okay, now, next part, what? Minus, right? Minus, because that's the formula. The minus, you have to remember, the first one's plus, then the second one's a minus. So I put minus, and now what number am I looking at? Negative 1. Hey, but it's negative, isn't it? So it's going to change it back to positive. But you had to account for that negative in there. So you'll have negative 1, but then times what? Another determinant, right? Now this determinant comes from hiding the middle column and looking at the, what, the 3, 4, negative 3, 1. So now I'm isolating my attention to these two with these two. Are y'all okay with that? I mean, it's easier if I go up there and physically cover up, and I've drawn too much crap on my... Okay, so if I actually physically come up here, I'm going to put the negative 1 down, or minus negative 1, cover that up, and then here's the 2 by 2 matrix I'm doing the determinant of, right? So what's that determinant going to be? 3 times 1 minus negative 3 times 4. A lot of times, like in my Cal 3 is usually when we do determinants like this. A lot of times I'll see students like with their finger like covering up columns and stuff, like, you know, like it's just part of the way you learn it. There's other ways to do it too, all right? This isn't the only way. So cover this up. What was it? 3 times 1 minus negative 3, right? Negative 3 times 4. So what does that turn out to be? It'll be 3 plus 12, right? 3 plus 12? That's what that's going to be. All right, let's go to the next one. We'll put it all together on the next line. Plus or minus? Plus, okay, and now we go to the last number here, 4. So I write that down, 4 times, now here's another determinant. This time I'm covering up this column, right? And working with the bottom 4 numbers here. Three times 0 minus 2 times 4. All right, let's put it all together. The first one we said, this right here was 2. So 2 times 2. Then minus minus is plus. 1 times, and then in there we got 15. And then plus 4, and then in there we got negative 8. Right? So 4 plus 15 minus 32, which is negative 13. There you go. Again, I apologize we can't get into, you know, the value of the determinant right now, okay? We can't. But at least you know how to compute one, so it's not like you're getting a class and, oh, we're just going to take the determinant. You're like, what the hell is a determinant? No idea. Just to see how your brain is thinking here, I just want to see what you think this might be. We're not going to, I would never ask you this. A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, A41, A42, A43, come on, A44. What do you think the determinant of that would be? Maybe I start with A11 and multiply it times the determinant of this 3 by 3. But what's the determinant of a 3 by 3? I would start with A2 and then do the determinant of these two and then go back and forth. Do you realize the magnitude of this problem now? Yes, because each one of these 4 things is now, each one of those 4 is its own 3 by 3 determinant, right? So that becomes, what's that? Yeah, well, because I'm covering up this column, this is the only 3 by 3 there, right? And then when I go to the next one and I cover up this column, then the only 3 by 3 left is these two, these and this, right? And then I go to the next one. You see it? I mean, it's a pattern. And what if you go to a 5 by 5? Now each one becomes a 4 by 4, but each 4 by 4 has 4 3 by 3s. Yeah. And then what it does is always switches signs. Yep.
By using this formula in that 3 by 3 box,
Uh-huh.
you just have to multiply by diagonally, right?
And this thing right here, you would have to do on that box exactly what we did on this problem. So it would be, that one box would be 1, 2, 3 other little steps. No. I just wanted you to think about, I'm not going to ask you to do a 3 by 3. I mean a 4 by 4, but there's kind of an algorithm that we're using to do this. No, that's too much time. That would take too long. Yeah. Okay. So I think that's probably it. Let me make sure no surprises here. Yeah, okay. We're going to move on. Chapter 13. No, this isn't a test. This is a review that one of my colleagues is using. So I'm just making sure I kind of brush through some of the things that they got through in chapter 12 and 13. Now, this next chapter, we did not cover all of chapter 12, okay? Just so you know. We only covered the first 2 sections and very lightly. Chapter 13 is titled Sequences Yeah, that's good enough. There's more, but we aren't even going to touch the rest of what this is about. Sequences. So how many of you have to take CalTo? CalTo? Okay, so you can look at CalTo as being 3 main parts. Calculus 2 has, the first third of the course is learning this thing called integration. After integration, you do applications of that integration. So you apply it to problems. And the third part of CalTo is sequences and series. And sequences is the beginning part of, I mean, really when we say sequences and series in CalTo, it's mostly series, but to do a series you must know what a sequence is. So this is our opportunity in a college algebra class to at least expose you to what a sequence is, the notation of a sequence, and that way when you get to CalTo, again, it's not like brand new. You've at least seen it before. All right, so let's look at the idea of a sequence. All right, so 13.1.1. A sequence is a function. But the domain is restricted to non-negative integers. All right, so before I can even continue, I need to make sure you understand what a non-negative integer is. So what are the integers? Do you all know what the integers are? Counting numbers like 1, 2, 3, 4, 5, 6, those are integers. That's not all of them, though. There's more. 1/2, 1/3, those are fractions. Those are rational numbers. Those are not integers. Nope. You're on the right track. 1, 2, 3, 4. But what about the other direction? So -1, -2, -3, -4. Those are integers. And 0. All right? So integers is the set ... -3, -2, -1, 0, 1, 2, 3. Those are your integers, okay? Does that make sense? That's all your whole numbers in both directions, positive and negative. A sequence is a function. Remember functions like x squared, right? X squared is a function, but we restrict the domain to only non-negative integers, meaning you are not allowed to plug in certain things into the function. You can only plug in integers that aren't negative. So what are the things that aren't negative? 0, 1, 2, 3, 4, right? So non-negative integers is this set 0, 1, 2, 3, forever and ever. So imagine now we take a function that we're used to seeing and we restrict its domain to just those numbers. What would it look like? So let me give you an example here. What if I take f of x equals x squared, but I restrict x to the non-negative integers? Man, there's got to be a better way of me saying non-negative integers, huh? Well, how do we say all real numbers? There was a nice letter that we could use. Remember the double struck R? Do you remember that? Meant all real numbers? There's actually another symbol that we use for integers. It's a double struck Z. It looks like this. Okay? A double struck capital Z. These are the integers. All right? Now, go back up here. These are the integers. How do I tell you non-negative? But zero's in there. Zero's in there also, right? There's different notations. If you wanted just the positives, like 1, 2, 3, you put a plus up here. A plus up here would mean all your positive integers, but I want to include possibly 0. So what we do is say something like this, greater than 0. I know that seems weird, but all the integers greater than 0. Equal, thank you, yes. Yeah, because I want 0, right? You could put z with a minus up here. What do you think that would mean? All the negative integers, okay? So, go ahead. I'm not going to ask you this. I'm just getting us to think right now. This is not anything like what you'd be asked for on the test. You could use this, yes. For what? Are you talking like this? Would that would be like the absolute value, right? That'd be basically take all the integers and make them positive, right? That would work. That would work. That's probably a notation that I personally don't see a lot, but I think from your background, there's different notations, right? This would make perfect sense. Take all these numbers, right? But absolute value, so it makes all the negatives positive, but that also includes 0. So different ways to do it, right? Okay, but the point of this is, what does the function look like? Now, do we know what x squared looks like? Parabola, right? So we would think this is going to look something like that, right? But you can only plug in 0, 1, 2, 3, 4. So let's plug 0 in. What do you get when you plug in 0? 0. What do you get when you plug in 1? 1. What happens when you plug in 2? You get 4, right? And then I can plug in 3 and I get 9. Normally, we would come in now and we would actually fill this in with our parabola, wouldn't we? But we can't do that because you're not allowed to plug in 1/2. Why? Because it's a sequence. With sequences, we do not want to plug in anything but the non-negative integers. So what your graph looks like is no longer nice and smooth and continuous where you can draw it without picking up your pencil. It's just a bunch of dots, right? It's a bunch of points, and there's a bunch of spaces and gaps between them. This is what a sequence is. A sequence is a function that's been restricted to just integers. So you have one input, one output, one input, one output, right? But all the stuff in between is left alone. All right? So let me give you another example. Or let me get some notation out of the way. Instead of writing f of x equals x squared with x in z greater than or equal to 0, or the absolute value around the z, however you want it. Instead of writing that, which seems like it's tedious to write that over and over, if I want to let you know this is a sequence, I'm going to write it a different way, a totally different way. I'm going to write it like this. A sub n equals n squared. That's it. So what is the difference here? Instead of writing f of x, right, f of x, I'm writing a sub n. The a is like the f. Okay, the a is like the f here. It's like, okay, this told you it was a function, right? What does the a tell you? This is a sequence. Instead of writing x in parentheses, we write n in a subscript. That's again telling you this is a sequence, and this is the variable. This is the thing that you're going to plug in, n. And what are you going to actually do when someone gives you that n? You're going to square it, which is what the other side said over here, right? You're going to square the x. But when you write it like this, n is assumed to start at 0 or 1. It depends. Sequences can start at 0 or 1, or you can start at 2. It doesn't matter, but the important thing is that the n is a non-negative integer. Does kind of make sense? So it's just notation. Just notation. Let me continue with this. Therefore, what would a sub 0 be? 0 squared, which is 0, right? What's a sub 1? 1 squared, which is 1. What's a sub 2? 2 squared, which is 4, right? A sub 3 would be 3 squared, which is 9. Yes? What you have created here is a sequence of numbers, isn't it? 0, 1, 4, 9. That's a sequence of numbers. Yeah? And I could continue on, right? I could keep doing this all day long. So let's look at something here. I'm going to get to a fresh note here. Find a sub n, which creates this sequence. I'm going to give you a list of numbers, and I want you to tell me what created it. Kind of like working backwards. If I gave you 0, 1, 4, 9, can you look at those numbers and tell me that came from n squared? Like go backwards. Let's see. So let me give you a sequence. So whenever we write sequences, we write a brace, and then we write out the list of numbers. So how about this? 0, 2, 4, 6, 8, forever. That sequence of numbers. What formula creates that? We're going backwards. So look at, Isn't this first one, it should be a sub 0, shouldn't it? This next one, a sub 1. The next one, a sub 2. Next one, a sub 3. Next one, a sub 4. So what we're saying is when I plug in 0, it needs to spit out 0. When I plug in 1, it needs to spit out 2. When I plug in 2, it needs to spit out 4. When I plug in 3, it needs to spit out 6. Do what? 2, not 2a, 2n. 2n. N is the variable. So a sub n here should be 2n. Do you agree? What happens if I plug in 0? A sub 0 is 2 times 0. 2 times 0 is 0. A sub 1 would be 2 times 1, and that would give you 2. A sub 2 would be 2 times 2, and that would give you 4. Do you see this?
So, like, you said the other formula was 2n squared.
Yes.
So we can, like, play with it, like, change it around, or because now it's n.
Oh, yeah, it's a function. A sequence can come from anything. I mean, like, you can have any type of sequence. We want to be able to look at a sequence and come back to this formula, if we can. Sometimes it's hard to. So this is the sequence. Make a little note over here. These are the even numbers, right? Even numbers. If I wanted to create a sequence of even numbers, I would use 2n, wouldn't I? Okay, let's do the same thing. I'm going to give you another list of numbers. I want you to see. I want to see if you can create this list. Can you come up with an a sub n for this? So let me help you try and think through this a little bit, since these are our first examples. This looks a lot like the previous list, doesn't it? Two plus n. This started, look, what we need, right? What we need is that when we plug in 0, right, we get -4. And then when we plug in 1, we need it to spit out what? -2. But aren't these still all the even numbers? They keep going up by 2 each time, don't they? So it's this formula, but not exactly. It's this formula with a slight adjustment. Instead of having 0, we need it to spit out what first? -4, which means we should take 4 away, right? Instead of spitting out 2, we need -2. So isn't that subtracting 4 again? This list down here is this list, just everything translated over 4, right? So if I use a sub n is 2n minus 4, that should work. I plug in 0, what does it spit out? -4. If I plug in 1, what does it spit out? -2. Do you see that? It's just a shifting of that list. Follow? Yeah. This starts to get to a point where it's hard to, like, teach someone how to see something. You know, it's like you see it or you don't see it. Yeah, it's not like here's the quadratic formula, just plug and chug, you know, copy me. That's what we call it, plug and chug formula. Just here's a formula, plug in the answer. I mean, there's not a whole lot of thought involved there. Okay, so here. I mean, yes, you got to get your signs right, and I'm not taking away from that, but it's a little harder to do something like this. How about this? Let's start it at 1. What are those numbers? Don't the odd numbers go up by 2 each time? Very much like the even numbers, right? In fact, isn't 1 just 1 more than 0 was? And isn't 3 just 1 more than 2 was? And isn't 5 just 1 more than 4 was? 2n plus 1 will create this formula, right? Or will create this sequence. So a sub n is 2n plus 1. Y'all see it? That creates odds, starting at 1. Can you create this one? Okay, what's that? A sub n equals 2n plus 7. Does that work? Plug in 0 first, what do you get? 7. Plug in 1, what do you get? 9. Plug in 2, what do you get? 11. Right? Right? You, yes. You're not messing with these, no. You're saying, I need to be able to plug in 0 and get 7. And to do that, here's what I need, this formula. That's going to give me 7. Now, I need to know that when I plug in 1 now, I get what? 9? Does it work? Yes. Do you see that? The formulas get harder and harder, as you might imagine. Right? Let's just keep doing some more, and I'll put you to the test. Okay? Let's just keep practicing with some stuff. How about this one? Create this sequence of numbers. Call up Gauss. Let's call Gauss. See. So let's just think about what we want. We want that when we plug in 0, it spits out what? 1. But when we plug in 1, we want it to spit out -1. And when we plug in 2, we want it to spit out 1. We plug in 3, we want it to spit out -1. How are you going to do that? Any expression you want. A sub n can be anything you want it to be here. It has something to do with -1. What do we know about -1? If you raise -1 to the 1 power, what do you get? No, to the 1. What's anything to the 1? Itself, right? What's -1 squared? +1. What's -1 cubed? -1. -1 to the n does it. -1 to the n, right? Okay, so let's try this. What's a sub 0? Is -1 to the 0? What's anything to the 0? 1. Okay. Then you plug in 1. What's -1 to the first power? Itself, right? And then when you plug in 2, a sub 2, you get -1 squared, and you get 1. And so this is going to alternate back and forth, 1, -1, 1, -1. This is called an alternating sequence. Does it make sense why they call it an alternating sequence? It's changing signs. All right, let's try another one. This is fun, right? The 3 dots means this just keeps going following that pattern. Well, is this the same problem? What's different about it? Any ideas of how we can do this then? How? I want every one of these to change, right? Its sign. So I really just want to take this and multiply it by what? -1. Multiply this one by -1. Multiply this one by -1. Yes? That would just change the sign, right, of each one? Right? If you multiply something by -1, it changes its sign. That's all I want to do is change the signs of this sequence. So all I need to do is take this and multiply the whole thing by -1, right? Let's just see if it happens. A sub n, I'm going to take the formula that was there and multiply it by -1. So here's the formula that was there, right? And you multiply it by -1, and that's what this is, yes? But we all want to get better and become calculus students. We understand that when you have two bases that are the same, and you have different exponents, you can put these together, and you can do what with these exponents? How? Add them. So this is the same as what? -1 to the n plus 1 or 1 plus n. Isn't it? Now what happens? Try it. Plug in 0, and you get -1 to the 0 plus 1, but that's -1 to the 1, which is -1. So now the first one that comes out is negative instead of positive. All I had to do to make that happen was tweak the formula. Tweak this power and make it an n plus 1. So take a step back for a second. I want you to look at this. Alternating sequences are extremely important in calculus. So if you want to create an alternating sequence that starts with a positive 1, right? You need to make sure that you're going to get a 0 out first, right? So just letting it be n worked. But if I want it to start with negative, I need to actually shift it just once so that when I plug in 0, I don't actually get 0, I get what? 1. And then when I plug in 1, what will happen? I'll actually get a what up here? An even, a 2, right? And then when I plug in 2, I'll get a 3, and then when I plug in 3, I'll get a 4. All right. I think you just have to be continually exposed to this until it starts to sink in. How about this one? One, 2, 4, 8. Ah, shit, I forgot to alternate it. How about that? Now we're starting to get into some interesting things. So let me help you a little bit. I'm not going to do the whole thing for you. When I look at a sequence, I always look to see first, is it alternating? Is this one alternating? Yes, it's going positive to negative, positive to negative. As soon as I see its alternating signs, I know automatically my formula must include this. Now, it might be n plus 1. It might just be n. I need to check. When I plug in 0, I need the first one to be a what? Positive, right? Positive. Don't forget the numbers here, just the signs. I need it to be positive. If I plug 0 into this, am I going to get positive? -1 to the 0 is 1, so that'll be positive. Yes? That takes care of the alternating signs. Now, tell me how you generate that list of numbers. 1, 2, 4, 8, 16, 32. Are those squares? Those evens? Those aren't evens. You're missing 6, you're missing 10, you're missing 12, you're missing 14. Those aren't evens. Those aren't squares. 8's not something squared. 4, it goes up by, well, doubled each time, yeah. 2 I think what you want to say is right, but what you're saying isn't right. 2n means 2 times n, right? Is that what you're saying? 2n? No. No. You said it doubles each time. Do you remember something that we talked about in this class that the bacteria, right? Like doubled each day, tripled each day? That was an exponential. No, that's not an exponential. Exponential, where's the variable? In an exponential function, where's the variable? It's in the exponent. So 2 to the n power. 2 raised to the n. Look, each of these is a power of 2. Now, I didn't want to write it down because I didn't want to give it away. This is 2 to the first power. This is 2 squared. This is 2 cubed. This is 2 to the fourth. This is 2 to the fifth. Now, forget the negative and the switching signs. We've already taken care of that, right? What is this first one? If we're going to follow the pattern, that better be 2 to the what? And 2 to the 0 is 1. So this should be times 2 to the n. Right? I don't know if that's what you were saying. You said 2n. 2n means 2 times n, not 2 raised to the n, which is totally different. So let's just check it. I mean, does this look like it's going to work? Right? What would a sub 0 be? Negative 1 to the 0 times 2 to the 0, which is going to be 1 times 1, which is 1. So that first number works. Let's check 1. A sub 1. Negative 1 to the 1, 2 to the 1. What's negative 1 to the 1? Negative 1 times 2? Negative 2. So that one works. The next one better be a 4. It will be, right? Do I need to check it? It's okay? Yes, now we have to look at this back here. Our formula works, right? But can we clean it up? Can we make it look any different? Absolutely. We could. We could if we wanted to. Since they're both to the n, you could put them both in a single set of parentheses to the n with multiplication between them. Because whenever you have two things being multiplied raised to a power, you can put the power on each one, right? Which is what this is. I'm going backwards. And then what's negative 1 times 2? Negative 2 to the n. So the formula for this, the most clean form of the formula is negative 2 raised to the n. And we keep going. I want to push you. See how much this thing's got left. 25%. This is like a puzzle, right? It's like a puzzle. All right. So let me assist you on this, the way that I think it's wise for you to approach this. First thing, is it alternating? Yes? Okay, does it start with a negative or a positive? Negative. How are you going to make that happen? Your formula must include what if it's going to alternate? Negative 1 to the n. It's either going to be n or n plus 1, right? If we're going to start at 0, right? If n is going to start at 0, and I need this first one to be negative, that's not going to work, right? That's going to give me a positive. So if I put plus 1 here, Now when I plug in 0, I'll get that negative to come out. And the one after that will be positive, then negative, then positive, negative. Understand that part? No? No? If you plug 0 in right here, what do you get? Negative 1 to the 1, right? What's negative 1 to the 1? Negative 1. So that'll create a negative out here, right? If you use just n instead of n plus 1, then when I plug in 0, it gives you 1, but you don't want it to be 1, you want it to be negative 1. So you have to put the plus 1 there. Does that make more sense? Okay. It's either going to be n or n plus 1, depending on where it starts. Okay, that part of it's done. Now, times, I have a fraction, don't I? This is a fraction bar. Can anybody tell me the pattern of the numerator of this thing? Forget the signs, right? The positive, negative doesn't matter anymore. What is it? What are these? Yes, it adds 2, but these are odds, right? How do we create the odds? 2n plus 1? That's what we use to create the odds. But we need to start at 3. 2n plus 3. Look, forget the 3's there. What does 2n create? What does 2n create? 0, 2, 4, 6, 8, 10, 12, right? It creates the evens. But if we add 3 to it, instead of creating 0, 2, 4, 6, 8, 10, 12, it's going to create, instead of 0, it'll create 3, right? Instead of 2, it creates 2 plus 3, which would be 5. Make sense? It's taking the evens, just adding 3 to each even number, and that should create this list. That takes care of my numerators, right? How about the denominators? 4 to the n? Almost. Almost 4 to the n. This one's tricky. It's almost 4 to the n. The problem is this. When you plug in 0, what are you going to get that first time through? You get 1. You don't want it to be 1. You want it to be what? 4. So, wait, say this again. This is 4 to the first power. This is 4 squared. This is 4 cubed. This is 4 to the 4th. So what you want is when you plug in 0, you don't want this to be 0. You actually want it to be a what? You want it to be a 1, right? And when you plug in 1, you want it to be a 2. And when you plug in 2, you want it to be a 3. So n plus 1 will create that formula. Difficult, very difficult to teach this. You're creating formulas from, you're finding patterns in numbers and generating formulas from those patterns. Oh, no, this takes a while in calculus, too. I'm exposing it to you because I want to help you in CalTo. I mean, in CalTo, I would spend an entire day or 2 on this. Because this is very important. If you can't pick this up, you can't do anything else later. Yeah. This is okay. So here was my Cal 3 exam that I gave yesterday. And this is one of the problems that they had. Okay, so these numbers, 2/9 minus 4/27 plus 8/81, blah, 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 they add up, keep adding those up forever and ever, never stop. And it actually adds up to be a number, like a finite number, okay, which we talk about in calculus. But the first step of this problem for the Cal student is this. Convert this into this, this is actually called a series because it's not just a sequence of numbers, they're being added and subtracted. But I want you to look at it the way that we just did. Act like this was just numbers, okay? What's the formula that would create this? Well, you want to start with positive 1, and then positive, then negative, positive, negative. So you want it to be -1 to the n, right? That'll create your first one will be positive. And then times, we have fraction. What's going on up top? These are just, are these evens? No, these are not evens. This is 2 to the first power. 2 squared, 2 cubed, 2 to the fourth, right? That's just 2 to the n plus 1. Because you need it to start at 1, right? You plug in 0, you need to start at 1. Then what about the bottom? This is 3 squared. This is 3 cubed. This is 3. So the first one there is 3 squared, right? So you need 3 to the n plus 2. Why? Because you need to start at 2. And we're plugging in 0 to start, right? So when I plug in 0, I need that to be a 2. And when I plug in a 1, I need it to be a 3. That's the first step of that problem for the calculus student. What's that? No, this is CalTo. Yep. Well, then we have to convert it to what's called a geometric series, and then we have to use a formula. But it's not that bad. Yeah. So, but that's the value of this. Let's see, the next question they had, does this series converge or diverge? So again, they had to come up with a formula for this. And then after that, notice that everything else in this test, they have the formula already, and they have to determine something else. So the formula is given to them. This is the formula that we're working with. And then they have to determine stuff from that formula. Here's the formula they're given. And that's different. Yeah. So here's the formula they're given. So you know how I'm asking you to look at a pattern of numbers and get the formula? Yes? This part of it is the formula. That we're going to talk about the exclamation mark. I think as soon as I'm happy that you've seen the pattern stuff. No, that's not integration. All right, I'm trying to think if there's any others that I want you to see. I've got the alternating, I've got the fraction, I've got the powers, evens, odds. That's pretty much most of what you'd see. All this does is makes your sign change. Yep. So once you've taken care of that part, you can totally ignore the plus minuses up here and just look at the numbers themselves. Okay, how about this one? I like to give this one because students will be like, what? 1, 2, 3, 4, 5. A sub n equals almost n, what? N plus 1. Because you start at 0, right? You plug in 0, you get 1. You plug in 1, you get 2. You plug in 2, you get 3. So it's just going to count out the numbers, right? Okay. So that's not a complicated one. Sometimes the ones that aren't complicated confuse us because they're so, they're so simple, they're hard, That's it right there? Okay. All right. 12. I'm running out of time. I'm not going to do recursive. Am I on 11 or 13, 1, 3? Okay. Mhm. So what is this? Is this? It's 5. Damn it! Right? It's not. You don't yell it, right? That's not what it is. So we have an operation that comes up a lot in statistics, especially. It's where you have to repeat multiplication. Let me motivate this with an idea. Let's say we have a combination lock. Let's say it's only 3 dials on this combination lock. Each of them 0 to 9, right? 0 to 9. Then how many different combinations are possible? How many different combinations can be put here? How many different numbers could you possibly have here? Include 0 though. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 would be 10. So 10 here, 10 here, 10 here. 10 times 10 times 10, 1,000. There's only 1,000 possible combinations on a 3-dial lock, right? You add one more, you've got what? 10,000 now. Just multiply by 10. So we're not to this thing yet, all right? That's a way you can figure out how many different ways that could happen, right? Now, let's talk about Kentucky Derby just happened, right? There were a bunch of horses, right? How many horses? I don't know. Anyone know? Let's do it a different way. Let's make this a little easier. Let's say we have 4 people. Okay, I need 4, 3 is kind of boring, so let's go with 4. Let's say we have 4 people. All right, we have 4 people, and y'all are going to race. Okay, all right. How many different ways can they finish the race?
If they actually finish it.
So let's see here. Yeah, assuming you can run the 30 feet that the race is. So here's first place, right? Here's second place. Here's third, and here's fourth, right? Okay, so how many different ways could the first place happen? Well, it could be any of the 4 could win the first place, right? So it could be 4. And now how many ways can second place happen? Well, there's only 3 people left now, right? Because one of them's got first place. So there's only 3 people that could possibly get, that'd be 3. How many ways could the third place happen now? 2 different ways, and that forces only one way to have 4. I mean, to fourth place. Okay, so how many different ways can it happen? You multiply this times this times this times this. Just like we did 10 times 10 times 10 times 10. You do the same thing. 4 times 3, which is 12 times 2, 24 times 1 is 24. There's 24 different ways. So we put these 4 guys in a race. There's 24 different ways that they could come across the line. Okay? So if you have 12 horses in a race, how many different ways can 12 horses come across the line? 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now who wants to write that out? Nobody, right? So what we do is we use an exclamation point to represent that multiplication. 5 with an exclamation means 5 times 4 times 3 times 2 times 1. That's what it means. It's just notation. And what it is called is factorial. It's called the factorial. So it's kind of like, you know how back in the day when you're learning like, hey, 2 times 2 times 2 times 2, we could write that as 2 to the 4th, because who wants to write 2 times 2 times 2 times 2? It was like a condensed notation, right? Exponent notation is just another way of representing repeated multiplication. Factorial is just a notation that represents a certain type of multiplication. That's all it is. Okay, so with that in mind, let's come up with the general definition for n factorial. N factorial, by its definition, should be equal to, and I'm going to put a number underneath this to help us, 9 factorial underneath. What's 9 factorial? 9 would come first, right? So what would n factorial be? First thing would be n times, now times what happens after 9? I have 8, right? So I need to subtract 1 from n. That's the next piece, right? And then the next one is going to be times 7, which means I need to take that n and subtract another one, which would be n minus 2, wouldn't it? So it's like you start with n, then 1 less than n, then 2 less than n, then 3 less than n, and you keep doing this until you get down to what? Not 0, 1, right? You keep taking 1 away each time until you get down to 1. Yes. N minus what? Well, but we don't know what n is, right? If it was, yeah, this keeps going, times 6, times 5, times 4, times 3, times 2, times 1. Yes? But this one, we just need the dot, dot, dot. You see this? Times, dot, dot, dot. That's me saying continue this pattern until you get to 1. That's n factorial. And the way we say that, n factorial. That's exactly what I was going to say next. Okay. N must be a non-negative integer. Also, what is that? Is it outside? Also, 0 factorial is, what do you think? 1. Yes, and it doesn't make a whole lot of sense. It's by definition, okay? We define 0 factorial to be 1. That's the only one that doesn't make sense, and I'm not going to get into it right now. There's a reason why it has to be 1. I can't, unless you do graduate school and you do like higher level math, I don't think, because there is a way to define factorial. There is even a way to define it on fractions. You use what's called a gamma function. And when you use the gamma function, when you plug 0 into the gamma function, you actually get 1. So 0 factorial has to be defined to be 1. You Google gamma function, you'll look at it and go, what the hell is that? Yeah. Okay, so let's do an example. I want us to simplify (9 factorial over 6 factorial times 3 factorial. Now, you could just do 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, couldn't you? Yes. So I'm gonna do it that way first. This is just 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All over, what's 6 factorial? 6 times 5 times 4 times 3 times 2 times 1. Now, what's 3 factorial? 3 times 2 times 1. Do you see that? This is 3 pieces. 1, 2, 3. Yes? All right. It's all multiplication between everything. I can cancel anything I want, but I can only cancel 1 on top and bottom, like 1 of each. Okay, so I'm going to go, what, 6, 6, 5, 5, 4, 4, 3, 3, 2, 2, 1, 1. Anything else cancel? No? So I get 9 times 8 times 7 over 3 times 2 times 1. But wait a minute, 9 divided by 3 is 3 times 8 divided by 2 is 4, and 7 divided by 1 is 7. So it's 12 times 7? 84. Yeah? There's another way that's not easier but smarter. Okay? Let me show you the other way. Same problem. 9 factorial over 6 factorial times 3 factorial. Okay, now watch what I'm going to do here. Can what? Nope. Can't do, yeah, you cannot do 9 divided by 6 here, and that's, 3. Nope, can't do that either. Nope. So watch, this is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 6 factorial, exactly. Right? This 6 factorial means what? 6 times 5 times 3 times, it covers the rest, right? The factorial symbol here is only on the 6. Do y'all see that? That's right. It's going to shortcut our canceling. Okay? Now I can cancel the 6 factorial and the 6 factorial. All right? Which is exactly the same. Now the next step, you still have to realize 3 factorial is 3 times 2 times 1, and then do your simplifying. Understand what we just did? Sure? Because I'm about to really see if you understand what we just did. What was it again? 84? I won't go through the work. All right. So just when you think you're feeling decent about this, I would like for us to simplify this. What is n plus 2 factorial over n minus 1 in parentheses factorial? So look, the factorial symbol is on everything that's in the parentheses here, right? The factorial symbol is on everything that's in the parentheses here. Simplify this. You don't know what n is. No one's going to give you n. Yes. I think you're on the right track. Hold on. What was the definition of n factorial? Whatever's here, right? Whatever's the factorial is on, you start with that, right? Then you multiply by whatever was there, take away 1. Whatever was there, take away 2. Whatever was there, take away 3, right? Yes? So can I rewrite this as, well, what's there to start with? N plus 2, right? Times, now take 1 away from that. So subtract 1 from this. N plus 1, right? Keep going. Now, I could say factorial right now, but I want to keep going. Take 1 more away. N plus 0, which is just n. Take 1 away again. When do I stop? Now. Why? Because what's on the bottom? N minus 1 factorial. You see how we did this just a second ago? Why did we stop at 6? Why did we stop at 6 here? Because it would cancel down here, right? I peeled off a 9, then an 8, then a 7, then the rest of it, right? The rest of it, I didn't write out because it was going to cancel with all this down here. I just did the exact same thing here. I had something on top that was bigger than the bottom, right? This was like the 9 and the 6. So what happened was I first wrote out the 9, then the 8, then the 7, and then what? This is like the 6 factorial, which cancels with this one. So when these cancel, you're left with that, n plus 2 times n plus 1 times n, which you could FOIL it all out, and that would just be a polynomial in n. You'd FOIL that out. Yeah. Just multiply it, or you could just leave it. But if you expand it out, n cubed plus 3n squared plus 2n, that's what you would get if you multiply it out. No, that's not extra credit worthy. Okay, so what do you think? All right. I try and we're probably ready to get in. We could do that. There's some issues with that though. There we go. Oh, there's no. I'm trying to find a problem here from my CalTo that has it. There's a factorial. Okay, so look, for what values does this thing converge? So who cares what it's asking? I just want you to see this step right here in the algebra. They wind up with an n factorial up here, and down here an n plus 1 factorial. And the next step, they cancel. What happened here? They rewrote n plus 1 factorial as what? N plus 1, then take 1 away, right? N, and then stop there, factorial. Why stop there? Because you had an n factorial up here. Then they canceled. We just did that just now, didn't we? Something like this. Question? What happens when you take n plus 1? Well, look, we started here. What happens when you subtract 1 from that? You get just n, right? You get n plus 0, which is just n. Then if you did another one, then yes, you would have to, yeah, all right. Where are we? I think we're done. I think that's all I can really do. So you have 3 exams to start looking at. Like I said, I posted all the keys to all 3 exams on our website on Canvas. I'm going to come up with something for you to review for the systems of equations. I'll come up with something. I'll put that out there for you, hopefully before next class. And then it'll also have stuff with these sequences and some of the factorial stuff. Okay? Thursday will be all review. But, I mean, come with questions. I'm not just going to stand up here and be like, okay, you know, I mean, I want you to have like, hey, you know, can we address this? Okay? Everyone have a great rest of your day.